Are we ready to start again? Okay, so this is a talk which I've used on other occasions. So some of it will be redundant, and it's perhaps a little more flashy than a lecture normally is. Anyway, what I want to think about is that what we've talked about is epistasis and imprinting and maternal effects, basically complications to the genetic system. But earlier on, and in much of science to this day, and indeed we have to use science, we use a reductionist, in science we use a reductionist approach. That is, can we get rid of all of this junk and look at just what we're interested in? And this shows up in evolution when we see things like, when we talk about multi-level selection, Williams' principle of parsimony. In explaining adaptation, one should assume the adequacy of the simplest form of natural selection, that of alternative alleles in Mendelian populations, unless the evidence clearly shows that this theory does not suffice. This is exactly the idea of looking at very small units and trying to trim off everything else. Indeed, Williams goes on to say that if we're going to talk about what genes do, ultimately we can look at each individual gene in isolation. This is an extreme view. That he says, no matter how functionally dependent a gene may be, and no matter how complicated its interactions with other genes and environmental factors, it must always be true that a given gene substitution will have an arithmetic mean effect on the fitness in any population. I hope what we've showed you today in the last couple of days is that that might not be quite true. Nevertheless, it's an essential part of research to do reductionism. And this was the early idea in the 60s and 70s of how we do reductionism. We're going to reduce to a single gene, and we're going to say, what is the effect of that single gene? And of course, anytime you do reduction, use a reductionist approach, it's going to be an approximation. And the question always is, how good an approximation is it? And always we have to be sensitive to that idea. Of course, the real world is more complex, and I just put this up to give some ideas that indeed it does. I showed a bunch of different kinds of interactions. This is between two traits. This is the performance of an aphid on two different species. And this is the correlation between father and son in height. Okay, so this was really what Sir Ronald Fisher did. And as we point out, Fisher was a brilliant person, but he developed his model on the assumption that traits are determined by a very large number of loci, a very small effect. The populations are very large and unstructured, and that mating is approximately random. So if we imagine that we have a giant population in which there are no interaction, in which there can be in which mating is random and interactions are random, and genes have very small effects, then in fact we can ignore epistasis, we can ignore maternal effects, we can ignore imprinting. Fisher was not aware of imprinting and may or may not have been aware of maternal effects, but he was certainly aware of epistasis. And in fact, he's the person who coined that term. However, because he was dealing with a large randomly mated population, he said we can ignore it. It will come out. It is, in fact, going to be part of the error variance, and it's something that isn't going to contribute to response to selection. And I just put up, this is Fisherian quantitative genetics. The implication of Fisherian quantitative genetics is that H squared will be heritability will be effectively a constant. It's really one of the very bizarre things about his infinitesimal model, that because there's an infinite number of alleles of infinitesimal effect, selection doesn't end up changing gene frequencies. And it's just an odd consequence of how that system works. Anyway, the reality is, you know, as I keep pointing out, the nice thing about quantitative genetics is that it works. And here's a classic Robertson's 1955 selection experiment on Drosophila melanogaster, and what he did is selected for large and small thorax length, and we see that it's an approximate linear response. If it was a straight line, which is approximately, that would imply that variabilities are constant. And as I say, it seems to work pretty well. Okay, but anyway, Fisher's model assumes very large populations and random mating, and if those are true, then we can simply ignore interactions among individuals. We can ignore interactions among genes, between generations. All of these things just go away. They become unimportant. And they're still there, but they just don't contribute to evolutionary change. However, we would like to relax that, and that's what we're trying, you know, what we've been talking about in this class. And that is, the easiest way to do that is to assume a metapopulation. And a metapopulation is a population of populations. It's really the very simplest way of relaxing it, because we have random mating within demes, and we have random migration between demes. So everything is quite easy to model, and we can have a movement between adjacent demes is just as easy as movement between demes, and things like that. Okay, so this is the space that Sewell Wright was talking about. And so I've told you a very little bit about Fisher. What I'd like to do is talk about Sewell Wright a little bit more. He was a geneticist who who was an undergraduate in Illinois, got his PhD with Castle, and then did most of his work at the University of Chicago and later at Madison. He did a lot of work with guinea pigs, and he was apparently quite interesting. Janice Spofford tells me that he did, in fact, he would bring in his guinea pigs to lecture, and he would line up the genotypes. If anybody's had a pet guinea pig, you know that if you put a guinea pig on the table, it won't leave the table. They don't jump. And so he'd have them lined up. And the story is that he would write on the board, and he'd every once in a while reach around and grab a guinea pig and erase the board with it. He denies it. Janice Spofford says it's true. Anyway, he did very in-depth reading of these guinea pigs. And he started thinking about the genetic architecture. Remember, this is back in the 1930s. We don't even know about DNA yet. And barely we know about genetics. And yet he comes along and he says all traits are polygenic, determined by a large number of genes, that there's universal pleiotropy. He says all genes affect all other genes. And he says that there's universal epistasis. I'm sorry, all genes affect all other traits. And he says there's universal epistasis, that all genes interact with all other genes. This is really pretty remarkable for the 1930s. And so, you know, today we have a more nuanced view, and we know that there are perhaps modules, so that there's sets of genes which interact with each other, but maybe don't interact with others. But at some level, we can accept this, that if you change one gene, you're going to have ramifications all through the genome. You're going to have ramifications all through you're going to have effects all through the appearance. And he said that what that means is that there are multiple solutions to fitness. There's multiple ways to be the most fit individual. And so, you know, to have a high fitness genotype. And so he came up with this idea of an adaptive topography. And the basic idea, and it's important to recognize that Wright was trying to come up with a metaphor with an image of what he thought was going on. In the real world is, of course, you know, he didn't pretend that it was reality, but it was a place to start. And what he imagined was that on these horizontal axes, and here I've got two, that you have some aspect of, he wasn't always clear, but it appeared to be something about the genotype. And on this vertical axis, you have fitness. And so you can have a large number of horizontal axes and one vertical axis, which is fitness. And then what he thought was, is this a pointer? And if so, which button is the right one? That's not the pointer. Here it is. Which is the rate?
I think it's the frontal one.
You got it backwards. Is it switched out?
Oh well, doesn't matter.
Are you plugged in?
If I had a weapon,
Here we go.
if I had a spear. Okay. Okay. So anyway, his idea was that, you know, this might be a high fitness mixture of situation where there's a combination of traits which give us high fitness. But the question is, how do we get from this sort of intermediate spot to other, you know, then these are other higher peaks over here, and they're separated by an adaptive valley. At least that's the metaphor he was using. So he asked, how do we get from a population which is at this low peak over to populations which are at much higher peaks? And that's really the fundamental question. And so what he did was he created his shifting balance process, or shifting balance theory as it's often called. And he suggested that there would be 3 different phases. A phase of random drift, a phase of individual or what he called mass selection, and a phase of interdemic or group selection. And to give you some idea, first of all we have the phase of random drift. And as I've drawn it here, we have a single large population, and he discussed single large populations. And he said, the problem with single large populations is that drift is very small, that there's very little drift because small populations, large populations don't have random changes in gene frequency. Individual selection is extremely effective, and individual selection, if you remember, always points uphill. And so our gradient is always going to be pointing to this highest peak. And while there may be mutation and recombination creating a distribution around that, selection is always driving to the center. And so what's going to happen is that this population is stuck here. It can't get off of that. In Fisher's world, there's no way to leave this and get over to these other points. And so he suggested that in his first phase, what we're going to do is we're not going to have a population, we're going to have a metapopulation. And these metapopulations are going to be, these subpopulations within this larger population are all going to be much, much smaller. As a consequence, we're going to have, you know, they will undergo genetic drift. And so instead of having a single population locked on that peak, genetic drift becomes dominant, and they will move around on this adaptive topography randomly. And this is an important idea that he had. There's no way that you can have, that you can move from one peak down slope by a deterministic process. Selection cannot make you go to lower fitness situation. The only thing that can get you down, to go downward on one of these fitness slopes, is a random process such as genetic drift. Now, of course, he recognized that the problem is that if you have a single population undergoing random genetic drift, the possibility of actually coming up with a better solution, it could happen, but it's very, very small. So he didn't think that a single small population had any hope of moving from one peak to another. But on the other hand, if you have a metapopulation, you have a large number of small populations. And so each of these small populations is a separate independent experiment, a separate independent drift, a separate independent exploration of the adaptive topography. And so some will stay pretty close to the original peak. Others will go down into the valley and maybe eventually go extinct. Other ones might come into where they start coming under the influence of one of these other peaks, which is perhaps a little bit higher. And so that's phase 1. And then he said once that happens, we're going to move into phase 2. And in phase 2, this is his phase of mass selection. What you have is natural selection is always going to drive you up the hill. And what these red arrows are supposed to be are selection gradients that are driving you up the hill. And the thing that's really interesting about this is that they are going in different directions. Because genetic drift has spread them out, they've come to different adaptive, under the domain of influence of different adaptive peaks. Some will be selected towards this peak, some will be selected towards this peak, and some will be selected back towards the original peak. And that was his idea, that the genetic drift is going to cause dispersion, that natural selection is going to drive you up to these various different peaks. And then finally, we're going to move on to the phase of interdemic selection. And the idea he had here was that you will get that if you have a population, which is, I'm imagining this is the high peak, on the highest peak here, it's going to be sending out migrants. His idea was that because it was at a higher peak, it would be producing more offspring, the offspring would be healthier, and that the population would get crowded and they would emigrate. This will be a net exporter of migrants. These will be, this population at the low peak will be a net recipient of migrants. And so the net result of that is that we're going to get migration towards we're going to have these high peaks be exporting whatever it is that makes them good to other populations. And we put those all together. Yeah, okay. We put those all together and that gives us our three phases. Now, there's a lot of controversy around this. And some of it's not in this, I don't have slides for. But you know, let's think of some of the problems with this. What does it take for genetic drift to work? Small population size and no migration. What does it take for phase 2 to work? Larger populations and selection. What does it take for phase 3 to work? It takes migration. And so these three phases are somewhat incompatible with each other. And yet all three phases, you would imagine, are going to work together simultaneously. And so there's been quite a bit of controversy around this. And in fact, Sewall-Wright and Fisher did not like each other very much. Anyway, we can sort of summarize the distinctions between these two people in this table here, which is from a paper which I did with, well, it's cribbed from a paper I did with Mike Waits quite a few years ago. What's interesting is that these guys were fighting, but they were fighting about things which were entirely different. They were arguing cross purposes, and I guess that's fairly typical. Because what Fisher was interested in is a refinement of adaptations. He was interested in agriculture. He was interested in how we get from, you know, I don't know, cows with low milk yield to cows with high milk yield. How are we going to improve that population? And essentially, he was treating cows, or Herefords, as a single very large population. And he was saying, how does that work? So he was interested in the refinement of adaptations, whereas Sewall-Wright is interested in the origin of novelty. He's interested in how did we get milk in the first place? How did mammals evolve milk as an adaptation? And that's the sort of thing that he was much more interested in. They saw very different processes of evolutionary change. Fisher really thought that populations were extremely large. It's almost comical to read how large a population he thought things were. Genetic drift had no room in his theory. What the source of variation was is mutation. New mutations accumulate in populations. And then natural selection weeds those out. And so you get these mutations which most are bad, a few are good, and selection throws out the bad ones and keeps the good ones. And eventually you get to that, eventually you get to a population that improves and refines the adaptation. On the other hand, Sewall-Wright is talking about the integration of genetic drift, migration, and selection. Genetic drift in phase 1 is for exploring the landscape. selection is going to basically augment that drift. It's going to give you, put you into different locations and put you on different adaptive peaks. And then migration is going to act as something which is going to allow beneficial combinations to spread. Evolution, again, Fisher saw it taking place in a large panmictic population. Sewell-Wright was talking about small subdivided populations. Genetic basis of evolutionary change. What those first quotes I was giving you were talking about is the idea that if everything is random mating and populations are very large, those interaction terms are removed. They get averaged out. And so the only thing that selection can act on is the average effect. And that doesn't change in his model. And so so selection only acts on these context-independent genetic effects, the alphas, but in a very large population, those alphas, the average effects, they aren't going to change. On the other hand, Sewell-Wright focused on epistasis and pleiotropy, and we could now add other things like maternal effects, as being central to his theory. Because that's what's going to, because if we were to look at a Fisherian adaptive landscape, it would be a single peak. Mount Fuji in Japan. That's a Fisherian adaptive landscape. Whereas the Andes is a more closer to a Wrightian adaptive landscape. Okay, and the process of speciation. Basically, the only way you're going to get speciation in Fisher's world is to have some sort of physical barrier to reproduction and disruptive selection. Now, Fisher was particularly fond of sexual selection as the form of disruptive selection. But it could be anything. It could be that they live in different environments and they adapt to different environments, eventually become so different that they become different species. Whereas Sewell-Wright felt that speciation was a natural byproduct of population subdivision. As populations went to different genetic combinations, and incompatibilities would naturally arise. Okay, and then, as I say, this controversy continues to this day. I mean, there's plenty of reasons why you should say Fisher is right and Wright is wrong. This is one of the titles, close to one of the titles I've always wanted to use. I wanted a paper that said Fisher was right. Why is Fisher right? Well, it works. It's a well-developed, very formal theory. It works, and when we look within a population, there's no reason. It can be cogently, successfully argued that yeah, epistasis is there. We don't have to think about it. It's not important. As